Hello students, in previous lecture we have discussed on the few theories which is related with the concepts of acid and base. That is first one theory, Arrhenius theory of acid and base, and second one theory, that is Bronsted-Lowry theory of acid and base. According to Arrhenius theory, acids are the substance or the species which gives H plus ion or hydronium ion. H plus ion when combines with water, it gives H plus ion combines with water to gives hydronium ion, and the species which gives H plus ion or H3O plus ion in aqueous medium are acids, while the base, it is a substance, it is a species which gives OH minus ion in aqueous medium. In aqueous medium are called as base. And according to Bronsted-Lowry theory of acid and base, acids are proton donors. That means they donate H plus ion, that is proton, to other species, and base, which are the species which are accepts proton, that means they are proton acceptors. Then now there are few limitations in the Arrhenius theory and Bronsted-Lowry theory to determine the few substances whether these are acidic or basic. Therefore, the new theory which is developed by Levys, that is Levys theory of acid and base. Today we are discussing on the Levys theory of acid and base. Then see here, according to Levys, acids are the substance or species which accepts share in electron pair. That means these are the substance or species which are electron pair acceptors. And the base, these are the substance or species which donates a share in electron pair. That means they are electron pair donors. Then see here, the concept of acid and base explained by Levys theory. Therefore, the acids according to Levys theory are called as Levys acids, and the base according to this theory are called as Levys base. Levys acid and Levys base can be explained by taking one example of it. See here, all of you aware of that ammonia. Ammonia that is having formula NH3, and when ammonia which having 3 hydrogen atoms covalently bonded with nitrogen atom which is present at the center, and that NH3 that is ammonia in which nitrogen has 3 valencies, and when 3 valency of nitrogen is completed, then it contains a lone pair of electron on nitrogen. All of you studied about that. The geometry of methane is tetrahedral, in which all 4 covalent bonds of carbon with 4 hydrogen atom, that is tetravalency of carbon, and that methane is tetravalent. Similarly, ammonia in which central nitrogen atom is there, which contains pure orbital in which 2 electrons are there and 3 hydrogen are covalently bonded with nitrogen. That is the pyramidal geometry of ammonia. Then see here, in ammonia, nitrogen possesses lone pair of electron, and here therefore it is a electron rich center of nitrogen in ammonia. It is a electron rich center in ammonia, and when H plus ion that means proton, the plus sign that means it is a cation, and as it is a cation, the plus sign on it indicates that it is a electron poor reagent. H plus is a electron poor reagent, and here when H plus ion combines with ammonia, then it gives, see here, the nitrogen in ammonia which contains lone pair of electron, and here H plus ion which does not contains electron to share or to form the bond with nitrogen. Therefore here both electrons of nitrogen shares between H plus ion and nitrogen of ammonia and forms a covalent bond, and that covalent bond is also known as dative bond or coordinate covalent bond, which is denoted by pointing arrow towards hydrogen atom. Then see here, there are now 4 covalent bond formation takes place, or 4 valencies of nitrogen are satisfied by 4 covalent bond. Therefore here nitrogen act as a electron pair donor. That means nitrogen in ammonia act as a electron pair donor. Therefore here ammonia is a electron pair donor species. Therefore it is a that electron pair donor species is known as base. Therefore here ammonia is act as a base, and H plus ion, that is proton, it accepts electron pair from nitrogen of ammonia. Therefore, it is an electron pair acceptor. Electron pair acceptor. Therefore, it is act as an acid. And here NH4 plus is formed here. That means, in short, we can write the same equation, that is chemical equation, like this. That is H plus I when combines with ammonia, it gives NH4 plus ion. When this electron pair which resides on nitrogen shares the electron pair with H plus ion and form the coordinate covalent bond or dative bond. And here ammonia is an electron pair donor. Therefore, it is a Lewis base. And here H plus ion is electron pair acceptor. Therefore, it acts as a Lewis acid. According to Lewis theory, here ammonia is a electron pair donor, therefore it is a Lewis base, and H plus ion, which is electron pair acceptor, therefore it acts as a Lewis acid. One more example I am going to discussing with you of Lewis acid and Lewis base. That is, see here, BF3, in which boron possesses 6 electrons. 6 electrons here. One covalent bond means 1 electron pair. Second covalent bond, third covalent bond is there. That means there are total 6 electrons around boron. Around that boron. And therefore here boron, which does not having 8 electrons in its octet, therefore it has incomplete octet. Incomplete octet, that means boron does not possesses 8 electron in its orbit or octet. Therefore it is a electron deficient species. And when ammonia, which is electron rich species, reacts with BF3, then here similarly NH3 combines with BF3 and lone pair of electron resides on nitrogen. It shared with boron to form the complex or coordinate compound, that is here between nitrogen and boron coordinate bond formation takes place and complex formation takes place. Therefore, in this example, ammonia is electron pair donor. Therefore, it is a Lewis base. And here BF3, as it is electron deficient, that means electron poor species. Therefore, it accepts electron pair acceptor. Therefore, it is a Lewis acid. That means, according to Lewis theory of acid and base, few examples are given here which explains the nature of acid and base of the substance. Using this concept, we can determine the acidic or basic nature of any substance. According to the strength of acid, we can classify these into two categories. Then see here, strong acids and weak acids. Strong acids and weak acids. Strong acids generally HCl, HBr, HI, H2SO4, HNO3 are the few examples of strong acids. Then weak acids, acetic acid, formic acid, citric acid, carbonic acid, H2CO3 carbonic acid, HF, H2S are the few examples of weak acids. And here similarly base can be classified into two categories like acids. These are strong base and weak base. Then see here examples of strong base, that is NaOH, KOH, LiOH, like examples of strong base, whereas NH4OH, ammonia, CaOH twice, calcium hydroxide, AlOH thrice, MgOH twice are the few examples of weak base. Then this classification, which is based on strength of electrolyte, strength of electrolytes. Then already you have studied about Ionic Equilibria. Ionic Equilibria. Then see here the strong electrolyte like HCl and NaOH. These are strong acid or strong base. HCl is a strong acid, whereas NaOH is a strong base. Therefore, these in aqueous medium dissociate almost completely. Therefore, complete arrow, full arrow is used here, and it gives more and more H plus ion or H3O plus ion in aqueous medium. Similarly, NaOH in aqueous medium, it dissociates highly or completely, and it gives Na plus OH minus ion in aqueous medium. And therefore, here in these type of aqueous solution of this substance, ionic equilibria does not present here. But all of you studied about that. Ionic equilibria is attained between dissociated ions and unionized molecule, and here in weak acid or weak base, for example acetic acid, it dissociates feebly and gives small amount of dissociated ions, that is H plus and CH3CO minus ions. and here equilibrium is attained between dissociated ions and unionized molecules of electrolyte. That means here example of weak base, that is NH4OH, it also dissociate feebly and very few molecules undergoes dissociation and it gives NH4 plus OH minus ions. Therefore, ionic equilibria is attained between NH4 plus OH minus ion and that is dissociated ion and undissociated molecule of NH4OH. That means it is now clear that here ionic equilibria is attained between or in the weak acid or weak base when dissolved in water. Therefore, here we can only apply law of mass action to the aqueous solution of weak acid and aqueous solution of weak base. Therefore, we can get the new constant, that is dissociation constant of weak acid and dissociation constant of weak base. Then see here HA, that means it is a general formula for any acid. Therefore, HA, let us consider HA is a weak acid. When it dissolved in aqueous medium, it dissociate to gives H plus A minus, and ionic equilibria is present in dissociated ions of acid and unionized acid molecules. Then applying law of mass action to above ionic equilibria. Therefore, we can get Ka is a dissociation constant of acid, that is Ka is equals to concentration of H plus into concentration of A minus upon concentration of HA, or it can be written like this: Ka is equals to concentration of H3O plus into concentration of A minus upon concentration of HA. Then here the new constant which is obtained is dissociation constant of weak acid. Depending upon the value of Ka, we can determine the strength of that acid. If the value of Ka is higher, then that acid is strong acid, and if Ka value is lower or less, then that acid is a weak acid, or strength of that acid is less. That means here the value of dissociation constant of acid determines the strength of that acid. Dissociation constant for weak base. For any base, the general formula for base is BOH. See here, BOH is a general formula for any weak base or any base. When base dissolved in water in aqueous medium, it dissociates to gives B plus OH minus ion. And ionic equilibria is present between dissociated ions of base and unionized molecule of base. Then apply law of mass action to about ionic equilibria. Then therefore here the new equilibrium constant which is obtained is a Kb. Kb is a equilibrium constant for dissociation of weak base, and that is also known as dissociation constant for weak base. Kb is equals to concentration of B plus into concentration of OH minus upon concentration of BOH. Then similarly we can determine the strength of base by using the value of Kb. If the value of Kb for that base is higher, then that base is strong base. And if the value of Kb is lower or less, then that base is weak base. That means we can determine the strength of acid on the value of Ka of that acid, and the strength of base can be determined by the value of Kb. From this we can define the dissociation constant of weak acid as well as dissociation constant of weak base. Then what is dissociation constant of weak acid? That is Ka. Dissociation constant of weak acid is equilibrium constant. Equilibrium constant of dissociation of weak acid in aqueous medium. When law of mass action is applied to the chemical equation or chemical equilibrium or ionic equilibria, when weak acid dissolved in given amount of water. And see here, similarly we can define dissociation constant of weak base, that is Kb. It is a equilibrium constant of dissociation of weak base in aqueous medium. That means when law of mass action is applied to the ionic equilibria obtained when weak base dissolved in given amount of water, then there is a relationship between Ka and degree of dissociation of weak acid, that is explained by Oswald dilution law of weak acid. Similarly, there is a relationship between Kb and degree of dissociation of weak base. That is also explained by Ostwald dilution law for weak base. Then we have discussed about the Arrhenius concept, Lewis concept, as well as Lowry-Bronsted concept of acid and base. Then Arrhenius concept of acid and base, which is expressed quantitatively by Ostwald dilution law. And about Ostwald dilution law, we will discussing in next lecture. Thank you.